So the aim of this talk is to discuss a couple of theorems that help us decide when a graph is not planar. So not planar means that it's impossible to draw it in the plane without edge crossings which are not vertices. So I'm going to start with a definition that actually goes back, I think, to 4.2 in the notes. I haven't written it down before, though we've used it implicitly, namely that of a subgraph. So let's start with the graph G. So a graph consists of a set of vertices and a set of edges. Actually, in this talk, we don't need the graph to be simple. I can even get rid of G here, but we'll just write G as a set of vertices and edges. Then a subgraph of G. Most important thing to say about it is that it's a graph. It has to be a graph. So in particular, that means that any edge has to go between two vertices. So let's call it G primed. It will have its own vertex set and edge set. And having said that G primed is a graph, all I have to say at this point is that the vertex that V primed is a subset, possibly equal to V, and the set of edges is a subset of E. Unless there are isolated vertices, if we took E prime to equal E, we'd get the same graph. So typically, E prime is a proper subset of V. So let me give you an example, rather than wasting more time. It's a very simple example. Let's start with G being essentially a force cycle. So I can draw a force cycle as a square, if I want to. So here's a picture of G, and let's label the vertices A, B, C, D. And I have to select vertices and edges, a subset of vertices and a subset of edges to define the subgraph. So I'm going to select A, B, and C. I could stop there if I wanted to, have no edges, or I could have one edge, or I could have two edges. Okay, so let me take both edges there. So I've selected vertices A, B, C, and I've selected edge AB and edge BC to get my subgraph G primed. Okay, so that is a subgraph. I can draw this in a simpler way, of course, because up to isomorphism, it's the same graph as what's called the path graph, just the vertices in a line. It's the same thing, A, B, C. So that is a subgraph of G. I just want to emphasize that we're not allowed, having chosen these two edges here, we're not allowed to leave out a vertex. So we're not allowed to have sort of A and B and not C, because we're not allowed to have an edge that doesn't join two vertices. So this is not allowed. That's not a subgraph. Nor can we have A and C like that. These are also not allowed. This is also not allowed. The reason this is not allowed, this last one, is that AC is not an edge in the original graph. So it can't be an edge in the subgraph. The other thing to say is that, as I sort of mentioned as I was going along, we could have this subgraph, we could have the edge joining A and B and C as an isolated vertex. That's a subgraph. That is a graph, so that's okay. The advantage of G primed, it's sort of neater, it's what's called vertex induced, because just the choice of the vertices, we've chosen all the edges that join the chosen vertices. So the subgraph G primed could be said to be vertex induced. That's another definition. Whereas here we've left out an edge, so this is not vertex induced. That's the notion of subgraph. Let me give you one other example. Maybe I can fit in the bottom here. If we take, say, K5, because we need to remember what K5 is in this talk. We take K5. What is K5? It consists of points around a pentagon, or you can draw it like this, or points around a circle for that matter, 5 points. And we need all possible edges joining any pair of vertices. Okay, so one way of saying that is that we've taken a pentagon and plonked a pentagram on top of that. Okay, so this is the graph K5, and I just want to make the point that the way I've just drawn it now is I started with a pentagon on the outside. That is a subgraph that corresponds to the 5 cycles. So if I just take these, if I emphasize the outside edges, these form a subgraph in which we have all the vertices. So this is a subgraph. So this has, K5 has a subgraph which is isomorphic to C5. I just say it informally, has a subgraph C5. That's the pentagon around the outside. But it also has another subgraph C5. It has the pentagram. That's another subgraph, as we've discussed before. Okay, so in fact it has 2 subgraphs, which are both isomorphic to C5. The second one being the pentagon, which, as I explained before, as a graph, the pentagram rather, as a graph, it's just, I saw this in the skills sessions as well as an exercise, it's also a 5 cycle. So there's a green 5 cycle and a pink 5 cycle. Those are both subgraphs of K5, and they both have the property that for both of them, V is equal to V primed. Okay, but they're not vertex induced because we're not taking all possible edges that there were in the original graph. Okay, now I want to come to a new definition. That of when 2 graphs are what's said to be homeomorphic. So let me go straight to that definition. So definition, I'm going to consider 2 graphs. Let's call them G1 and G2. So 2 graphs G1 and G2 are said to be homeomorphic. It's a funny word, unless you've done this in topology, come across this in topology. Maybe a new word for you, homeomorphic, not homomorphic, homeomorphic. Two graphs are homeomorphic if one can add vertices of degree 2 only to one or both graphs to obtain 2 graphs that are isomorphic. But basically we're saying that 2 graphs are homeomorphic if they only differ by vertices of degree 2. Okay, again, a simple example will illustrate this. Let's start with the cycle C1. We don't normally talk about this because it's not a simple graph, but that is a graph. It's 1 vertex and 1 edge that loops around. That's allowed. But I can add extra vertices of degree 2. I can take the same graph C1 and I can add as many vertices as I want of degree 2. Let's add 4 of them. So this would then be, if we regard the red dots as vertices, this would then be C5. And these 2 graphs are homeomorphic because they only differ by vertices of degree 2. What I have to do is I have to add to C1 the, well, it's not C1 anymore, but what was C1, I add vertices of degree 2 and I get C5. So I've added 4 vertices to C1, none to C5, and these are isomorphic graphs, so they're homeomorphic. And by that token, you see all cycle graphs, that means when you just put points around a circle or polygon, all cycle graphs are homeomorphic to each other. So you can't see that. All cycle graphs are homeomorphic. C1 is homeomorphic to C2, to C3, to C4, and so on. So this is a weaker notion. If graphs are isomorphic, they're certainly homeomorphic. You don't have to do anything to get them to be isomorphic. So isomorphic implies homeomorphic. So iso implies homeo, but not vice versa. Not vice versa. This is definitely false. So that's the notion of homeomorphic graphs, and that allows me to cite immediately. Well, perhaps I should add a bit more, particularly if you've sort of done topology. The idea here is that you think of the edges of a graph as being like arcs in space, in the plane or in space, and a vertex is just a single point. If you do that, it means that you can recognize vertices of degree 3 or 4 from the picture, even though you don't actually see the vertex. You don't see the individual point. You hardly see the individual point, sort of infinitesimal. But you can recognize a vertex of degree 3 or 4 or higher, but you don't recognize a vertex of degree 2 because the point is sort of hidden in the curve. So the idea is you sort of ignore vertices of degree 2. That's the notion of homeomorphism. So it's a very natural thing to do. Okay, but this definition allows me to quote Kuratowski's theorem. Kuratowski's theorem. Which says the following. Suppose we have a graph, any graph, G, and this is going to give us a condition for this graph not to be planar. So G is not planar. I'm going to quote it like this. G is not planar, not a planar graph, if and only if G possesses a subgraph homeomorphic to either K5 or K33, or conceivably both. Of course, you can put the two together and then it will have both. So that's Kuratowski's theorem, and it's quite a remarkable theorem. You see, it's obvious that if G has a subgraph homeomorphic to K5 or K33, then it's obvious that this implies that G is not planar. Once we know that, as we should already, that K5 and K33 are not planar, then the implication backwards is easy. So this is easy because K5 and K33 are not planar. And we've seen that, I've mentioned that before. For example, K5 is not planar because it doesn't satisfy this relation on the edges. Remember that for a planar graph with some conditions, some weak conditions, we have to have the number of edges is less than or equal to 3 times the number of vertices minus 6. That's not satisfied for K5. That's not satisfied for K5. It doesn't help for K 3, 3, but there's a similar thing it doesn't satisfy. Or you can use a diagrammatic proof. You see, for K5, this is done in the notes. For K5, K5 has to have a 5 cycle. I've said that before. It has a 5 cycle. If it could be drawn as a planar graph, that 5 cycle would essentially be points around a circle. It would have an inside and an outside. So you can start asking whether the other edges go inside or outside, and you get stuck when you try and add the 10th edge. So it's quite easy to see one way or another that both of these graphs, neither of these graphs is planar. But the interesting thing, that the hard part of the theorem is the converse, that we're saying if we know the graph is not planar, then it must contain essentially K5, if we ignore vertices of degree 2, it must contain K5 or K33. Incidentally, adding or subtracting vertices of degree 2 won't affect planarity. Okay, we can add vertices of degree 2 to our heart's content and K5 will remain non-planar. Okay, so let me give you an example. I'm not going to prove so this is hard. Let's say this is hard, this forwards implication. I'm not going to prove it. But we should certainly know the theorem. Let me give you a sort of classic example of an application of, or a demonstration, if you like, illustration of Kuratowski's theorem, and that consists of looking at the Petersen graph, which, as you know by now, is one of my favourites. So here's the Petersen graph, which again starts with a pentagon. So I'll do it like this. What did before? Okay. And then I have my inner pentagram. Total of 10 vertices. This is K. This is the Petersen graph. So my example of Kuratowski's theorem is going to involve the Petersen graph. This is exactly the same example as done in the notes. Now, the thing to notice is that I ought to remark here, we've begun to talk, I noticed also in the skills sessions, of degree sequences. So I want to remark that the Petersen graph has degree sequence. Well, all the vertices, there are 10 vertices and they all have degree 3. So it's a bit of a bore to write its degree sequence, but let me do that. There are 10 threes. 5, 6, 7, 8, 9, 10. That's the degree sequence of the, can't quite see it, of the Petersen graph. 10 lots of threes. On the other hand, K5 has degree sequence for 5 vertices, each of degree 4. So because of that, it's obvious that P can't contain K5, a subgraph homeomorphic to K5. So P can't have a subgraph homeomorphic to K5, because the only thing you're allowed to do with homeomorphism is add or subtract vertices of degree 2. Well, there are none to start with, and even if I start adding 2's, I can't get to this. So there's no way I can, by adding vertices of degree 2, get to K5. Okay, but I might be able to get to K33. So in fact, by Kuratowski's theorem, we know that's the only hope, because you might guess that P is not planar. It's fairly obvious, I think, that P is not planar. It's even more complicated than K5. So assuming we understand it's not planar, we guess it's not planar, it's got to contain, by Kuratowski's theorem, K33. It's got to contain a subgraph homeomorphic to K33. Okay, so we look for K33 up to homeomorphism. And I'm going to tell you how to do this. It's rather neat. It's done in the notes. First of all, we want to choose a subgraph. So we've got to restrict. We've got to choose a smaller set of vertices and edges. We're going to start by removing these 2 edges. Okay. Now, having removed these 2 edges, what that means is that if you remove this edge here, this vertex becomes and as does this, they become vertices of degree 2 once we remove this edge. Okay, so we can actually, this becomes a vertex of degree 2. So we could actually remove that as well, and this vertex as well. Similarly here, if we remove this edge, this becomes a vertex of degree 2, as does this. So we could remove that vertex and remove that vertex, still to get homeomorphic subgraph. So if I do that, what have I done? I'm sort of skirt round here. So I've removed that vertex. So I don't need to indicate that vertex anymore. And similarly here, I can skirt round that vertex and I can skirt round this vertex. So these vertices remain in our subgraph, as do these, and as do all the other edges. An edge going up there, this remains, this remains, this remains, this remains, and this edge remains. Okay, that's my subgraph. And it's a subgraph because I'm still using, well, it's no longer a subgraph because I've removed vertices of degree 2. It was a subgraph, then I removed these 4 vertices of degree 2, and that makes it homeomorphic to a subgraph. So what we've done here is that we've effectively removed from the Peterson graph, how many edges did we remove? Well, first of all, how many edges did we remove? 2 to start with, but then removing vertices essentially got rid of 4 edges. So we removed 6 edges altogether because 4 pairs of edges were combined into 4 individual edges. And we removed 4 vertices. So leaving, how many edges does that leave us? We started with 15, so it leaves 9 edges, and it leaves 10 minus 4, 6 vertices, which is exactly as for K5. Sorry, not K5, K33, which is what I'm after. And I claim this graph is K33. You can do that from the sort of idea of colouring. K33 has to be a bipartite graph. So if we colour this vertex alpha, these 2 vertices would have to be beta, as would this vertex, leaving these 2 vertices to be alpha. And that's okay, that's a 2 colouring because no alpha vertices are joined and no beta vertices are joined anymore. So, you know, we could put the 3 alpha vertices together and the 3 beta vertices together, and we've got K33 by joining all the alpha vertices to the beta vertices. There's 9, total of 9 edges. I've forgotten one. So the alpha vertices on the left and the beta vertices on the right. So you see that is K33. So that's the example of Kuratowski's theorem, and that proves, using Kuratowski's theorem, the conclusion, if you like, is that P is not planar, if you didn't know it before. As a consequence of Kuratowski's theorem. Okay, now time is running out, I dare say, but I have to talk about the second theorem, which is Wagner's theorem, which is similar to Kuratowski's theorem, proved a few years later, but it relates to a slightly more complicated notion, that of contracting the edges of a graph. Okay, so it's also going to involve subgraphs, but subgraphs in which edges have been contracted. Or we take anyway, let me explain the definition before I get muddled up with what it means. So let me start with, as we gave the definition of homeomorphism, I need another definition now which involves contraction of edges. So definition, third definition for today. Let G be a graph and with an edge, call it UV. So U and V are vertices of G. Then the contraction of G by the edge UV is the graph, it's the new graph, and it's, if you need, I'm not going to call this G prime, but it's sometimes denoted G slash the edge. It's a bit like some sort of quotient, some analog of quotient in other branches of mathematics. Is the graph formed by, have I said this, by coalescing the two vertices U and V. So you sort of make U and V join together. So if you like, by converting U and V into a single vertex, into one vertex, making them coalesce, and eliminating the loop that you would ordinarily get from the edge, eliminating the loop, and possibly any multiple edges. You don't want multiple edges left in this process, and the loop and any, there may not be any, multiple edges. I'll give an example to show what I mean by that. Any multiple edge should just become a single edge. So multiple should become a single edge. You don't eliminate it all, but it should become a single edge. So an easy example here, another easy example to illustrate this definition. This time I take even simpler than a square, I'll take a triangle. Okay, so here is the G. It's going to be, if you like, a 3-cycle, which I should draw as a triangle with vertices, well, let's put A at the top and U and V to be the bottom two vertices of the triangle. Now the idea is that you make U and V coalesce. So what would happen if these were pieces of string and you make U and V coalesce? What would happen is that you'd have the vertex A here. U and V would become a single vertex, draw it a bit bigger, but it's just a vertex. You'd get a loop here, and you get two edges coming down from A to the new vertex. But the idea is that we eliminate the loop. We don't want any loops, and we don't want any multiple edges, so the multiple edge becomes a single edge. So the contraction is just this graph here. So we have A, and we have a new vertex, I don't know what to call it, there. So this, in this case, this would be the contraction. This would be the graph, which I denoted G is UV contracted. So that's the idea, and you can I think it's easy to understand what I've done there. Now you can, let's say also one says, in practice we want to keep repeating this operation, do it with various edges on a graph. So one says that a graph, G can be contracted to G primed, say. So another graph, G primed, means one says that if G primed is obtained from G by a sequence of edge contractions. By a sequence, not just one, you can have 1, 2, or 3, and so on. By a sequence, you might only need one, but by a sequence of edge contractions. Okay, in that example, I can't do much more, but I could contract one more time and get a single vertex. So if I really wanted to reduce this, it's not very interesting. I could contract A and this new vertex. Let's call this W. I could contract A and W and get a single vertex, which has disappeared under my card. There we are. So obviously, if you've got a graph, you could contract everything and get a single vertex, but that's not a very interesting observation. Let me give you an example. Well, let me give you the theorem first of all. Just make sure you can see what I've just written. So now I'm now in a position to quote the second theorem of the day, which is Wagner's theorem, which has a similar flavour to Kuratowski's theorem. So Wagner's theorem, dating from about 1937. A graph G, as before, is not planar if and only if G contains, or G has, a subgraph that is contractible, can be contracted. That is contractible to either our two friends K5 or K33, or two enemies if you like, or both, or conceivably, sometimes, not necessarily, both. So yet again, what this theorem is saying, just like Kuratowski's theorem, is it's saying that somehow the presence, in some sense, the presence of K5 or K33, in this case it won't be quite as obvious because they're not, you don't sort of see them as subgraphs with up to vertices degree 2. You have to do some work to see them. But somehow their presence detects the fact that the graph is not planar. So if you think of being not planar as being like a disease, somehow you will always find one or other of these nasty graphs, if you like, present. That's what these two theorems tell you. Or if you think of being not planar as an attractive feature because it means the mathematics is more complicated, being not planar is signalled by the presence of one or both of these subgraphs, of these objects in some sense within the original graph G. Now, let me just remark that neither part of this theorem is entirely trivial. This part follows from this implication here, the forward implication, follows from Kuratowski's theorem. Because if G is not planar, it has a subgraph that is homeomorphic to K5 or K33, and it follows that that can be contracted to one or the other. But this backwards implication is not so easy to prove. So I just leave it like that. Let me finish with the sort of classic example, and this again is of the Peterson graph, in which you can actually see this theorem. So if we take the Peterson graph yet again, and it's in a pentagram. What are we doing? We're looking for a subgraph. Well, a subgraph could be the whole graph. So when I say subgraph, it could be or G itself, because G is a subgraph of itself. And in this case, we take the whole graph, and it can be contracted to K5. That's obvious, because all you have to do is take the spokes and contract them. So we have our 5 spokes there, and if we contract each one at a time, that means that we make the vertices coalesce. So if we contract first of all the top one, these 2 vertices coalesce, we don't get any loop, we don't have to worry about any multiple edges because these are not connected to other things. So if we just do the single contraction, we'll be stretching out the pentagram and we'll get back, and then we do each spoke in turn. So a total of 5 contractions, 5 individual edges contracted, and that brings us back to our graph K5. So that's another illustration of the fact by Wagner's theorem that the graph P, the Petersen graph, is not planar because it has a subgraph, namely itself, in this case, that can be contracted to K5. Actually, it has a subgraph that can be contracted to K33 as well in this case. So I won't write that down. It's an exercise in the lecture notes. So you can also find a subgraph that can be contracted to K33. I'll stop there.